I just want to say welcome back to the podcast, where we unlock the secrets of the universe one episode at a time. Today, we will be marking the start of our next topic, which is going to be section 3.9.2, classification of stars. So, let's start off with stars by luminosity. So, in the cosmos, not all glitter is gold. Or should I say, equally bright. Stars shine with varying intensities, leading astronomers to classify them by luminosity, using apparent magnitude scale. Right, so this scale, which was perfected by the Hipparcos satellite, ranges from the brightest stars at negative values to the dimmest visible with the naked eye at a magnitude of 6. But there's a twist, you see. The scale is logarithmic, meaning that a difference of only one magnitude actually corresponds to a brightness ratio of about 2.51. Why do you think astronomers chose this scale for brightness? So, consider how magnitude scale helps us compare the brightness of stars from the Earth's surface. This marks segment 2. Beyond apparent, the absolute magnitude. But how do we compare stars fairly when distance affects brightness? And absolute magnitude, a measure of a star's luminosity at a standard distance of 10 parsecs. It's a cosmic equalizer, allowing astronomers to truly compare stellar brightness. And with a magic formula, m minus m equals 5 log d minus 5, where d is the distance in parsecs, we can bridge the gap between how bright a star appears and how bright it truly is. What might this reveal about stars that appear dim, but are actually intensely luminous? So, think about the relationship between distance, apparent brightness, and true luminosity. How does this help astronomers understand the universe? This marks segment 3, which is temperature, black bodies, and spectral classes. So, stars are not just points of light. They're cosmic furnaces with temperatures that span thousands to millions of degrees. Through Stefan's law and Wien's displacement law, we learn that a star's temperature affects its colour and spectrum. So from blue to hot, O class to the cool red M class, each spectral class tells a story of temperature, colour and composition. These classes are not arbitrary. They're based on the star's absorption lines, the unique fingerprints of elements in its atmosphere. So, why is the temperature of a star so critical to its classification? So, a question for you. Reflect on how a star's colour and spectral lines provide clues to its temperature and composition. How does this influence our understanding of stars? This marks segment 4, which is the mapping of the cosmos, the HR diagram, or the Hertzsprung-Russell diagram. So one of the most powerful tools in astrophysics has to be the Hertzsprung-Russell diagram. It's a stellar census chart plotting stars by temperature and absolute magnitude. This diagram reveals the life cycle of stars from the main sequence to the final stages as dwarfs or giants. So the Sun, which is our closest star, sits comfortably in the main sequence, but each star's journey on this diagram is a tale of birth, life, and eventual death. So how does the Hertzsprung-Russell diagram help us predict the fate of stars? Question for you. Consider the Hertzsprung-Russell diagram as a roadmap of stellar evolution. So what can we infer about a star's past and future from its position? This marks segment 5, the dramatic endings. Supernovae neutron stars, and black holes. So, not all stars may fade quietly. Some end in spectacular supernovae, outshining entire galaxies before giving way to neutron stars, or the enigmatic black holes, where gravitational pulls allow nothing to escape, not even light. These cosmic cataclysms serve as cosmic milestones and standard candles to measure the universe's vast distances. They challenge our understanding of physics, with supermassive black holes lurking at the centre of galaxies, including our own Milky Way. How do these stellar phenomena expand our understanding of the universe? So, a question for you. Imagine the forces at play in a supernovae, or the mysteries harboured by black holes. What questions do these extreme objects raise about the nature of our universe? So, to conclude, our journey through the classification of stars has taken us from a humble twinkle to the cataclysmic end of stellar giants. Each star in the night sky tells a story of cosmic proportions, from its temperature and luminosity to its eventual demise. As we gaze up at the stars, we are not just looking at lights in the sky, we're witnessing life stories of the universe's building blocks. Keep your eyes on the stars, and who knows what mysteries you'll uncover. Thank you for joining the podcast. Until next time.